Okay, looks like we're ready. We're moving into the last third of the quarter of the course. So the first third was axial stress and strain and axial deformation. The middle third was flexural stress, so beams bending, also frames and machines were in there. And now the last third is torsion, so things are twisting, and a couple of other topics that don't really fit in the other categories. So smaller topics. So there's several small topics in the last bit here. So let's look at some of these. I probably have to switch this over. Let's see. There we go. So we also, last time, Monday, we talked about the group project, the trust project overview. So make sure if you haven't looked at that, go back and watch that and get your team. You need 3 or 4 people on your team. And we need to start forming those. I haven't checked email recently to see if anybody has like claimed a team or not. But kind of let me know once you've got your team so I can keep track of who is on a team and who is not on a team. So here's where we're going. We have a couple of lectures of torsion. Today we'll just start a general overview of torsion. Then we'll do angle of twist. So, you know, that's parallel to the axial deformation. And then we'll do some power transmission. That's actually the shafts are spinning now. So it may not look like statics because things are sort of moving. They're not translating though. They're just spinning in place. What we're not going to do is we're not going to combine our axial, flexural, and torsion. We're not going to do that. If you need that content, that would be the next course. Then we've got some thin-walled pressure vessels, so that's not torsion. That's Coke cans, airplane fuselage, stuff like that, that has a higher pressure inside than outside, or vice versa. Could have a smaller pressure inside versus outside. That's a little bit different process, but same idea. And then stress concentration factors by hand. So we've sort of done this. We haven't officially, but when we did the SolidWorks simulations, we looked at the stress profile on like a tensile test specimen or something. And that's the same kind of thing, but there is a way to do a similar approach by hand using some charts to get a higher stress than the average stress we've been calculating. We'll look at that later on. And then the last week, August 7th, I think I might have said the 8th in some previous lectures, but it's the 7th. You will have the option, you don't have to do either of these, but you have the option of either retaking exam 1, different questions, but same content, or the exam 2. And whatever you make on the new test score is the new grade that you have. So hopefully you do better. Most people do. Most people, the average improvement is, 6 points or so. Clearly some people get way better, but the average over the years that I've been doing that, the improvement's about 6 points. Very few, if any, people have ever done worse. I can't really think of anybody who's done significantly worse, maybe a point worse, but I don't remember anyone who's ever done significantly worse. And then Wednesday, we've got exam 3. It does cover all the content, so it will have stuff for all the way from the first day of class. Because the stuff we're doing now in the last third is pretty small topics compared to the things we've been doing. So that'll be exam 3. And then that Thursday, there's no actual class lecture. Actually, I guess there's no class on the 7th, 9th, or 10th. It's just the exams. The 10th is just the last day to turn in your trust project. All right, so torsion. We're going to look at torsional shear stress. So let's go over here. There we are. And let's see what we've got. All right, so like I wrote, this is a shear stress, so whenever we calculate this stress, we will compare it to a shear strength. So that's important to keep in mind because all of our materials that we're going to be dealing with, the shear strength is significantly less than the tensile strength. And the model that we're using is if we don't have a number for the shear stress in our charts that we can go look up material properties, then we will take half of the tensile strength. So if the tensile strength yielding is 36 KSI for a generic steel, then the shear strength of that same steel will be 18 KSI, half of it. There are different models you can use. You can, instead of taking 50%, you can take 57.7% in a different model. And it just depends on your application and what you're doing. We're taking the most conservative model, basically. All right. So our equation that we'll use is pretty straightforward. It will be tau because it's a shear stress. And it's going to equal T times rho, that's my version of rho, over J. So we've got some variables to define in order to deal with all this stuff. All right, so T is the internal torque. So that one's pretty obvious, T torque. This is the torque that is trying to twist whatever kind of shaft. We're only going to deal with round shafts. So they can be tubes, hollow on the inside, but they're round. So there's not anything, I'm looking around to see if I even, oh, here we go. We're not talking about something like this, where the shaft is a, what is that, a hexagon? Yeah, hexagon. So no, none of that. You could do that, but it is going to be a different, it's the same type of equation, but J, when we get to that, that'll be different. So only round cross sections, not hexagons or stuff like that. Only round. Actually, this is tapered, so this would be a little bit different. Let's go back here. So T is the torque that's applied. It's an internal torque, so it's not necessarily the ones applied to the outside. We do have to do the same thing that we've been doing, where we've calculated axial stress or whatever, and we cut the piece open to see what's going on inside the piece. We have to do the same thing here. Rho is the distance from the center. So these are all circles, so it's the centroid and center are the same thing. We'll put center of the shaft to the point of interest. So maybe if we draw a picture, let's just say we have the cross section of a circular shaft, so it's just a circle. Here's the center of it. That distance is rho. Or maybe this distance is rho. You know, if for some reason I wanted to know the stress inside there somewhere. Maybe I've got a hollow. So I wanted to know the inner diameter or something. You sometimes, just like when we were doing the bending stress and we had this value C, and we could do MC over I, you could sometimes see alternate equation, tau max equals T times C over J. Same idea, where the C is just the largest value of rho, so it's outer radius. It is a radius, it's not a diameter. So that's that. J is what's called the polar moment of inertia. Let's see if I can remember. Integral of rho squared dA. So you could, if you had a polar, because it's integrated, ends up d theta in the way you integrate it. It says dA here, but the area is, I think you would integrate, well, maybe you could integrate with a d rho. I'm not sure. Anyway, it is polar because it's round. We're only doing round ones. If you had to do another shape, then the problem with the hexagon shape cross sections and things like that is that you'll get stress concentrations at those edges where they meet. whereas a round circle, you don't get those concentrations. So there are sometimes reasons to have a faceted shaft. Maybe it's got to interface with something, and that's the way you're going to interface it. Like it's a drive shaft that plugs into a socket somehow, and if it was just a circle, then it wouldn't grab it. It needs to be some kind of shape. Those you have to treat a little bit differently. So if you were to assume that the circle, let's draw us another picture here without row on it, maybe a bigger one. Let's go ahead and give it an inner diameter. Trying to think of what the variables I want to use are. I think I want C here, which is not the same C that I just talked about, but I think they do use, most commonly use a C here and a B here. I might should check that before I write that down too much. I wonder if I have some notes here that well, let's just look up. I think most of the time you end up with a C as your inner radius. These are not giving me what I want. That one's using outer radius, outer. Well, you could do that, uppercase and lowercase d, but I think your book. I have your book. I think your book is mostly going to use B and C. Let me, before we go too far, let me make sure that that is true, because I don't want to use a different variable set from what your book uses. Let's see. Let's see, 361. Let's check page 361 here. Yes, so page 361, torsional shear stress, the elastic torsion formula. They have a diagram, figure 7.5, and it uses B as the inner radius, and oh, so they're backwards. Okay, so I did have them backwards. So that is the C that you expect it to be. B is the inner radius and C is the outer radius. So that's good. Now, we will apply the integral of rho squared dA to this. Sometimes, just so you know, I don't know if you remember, integral of y squared dA was the moment of inertia, sometimes called the second moment of area. This one is also a second moment of area, it's just polar. So the polar second moment of area. Okay, let's see. Since we are going to limit the shafts that we're dealing with to either solid round shafts or round tubes, so one or the other, then J for us will always be integral of pi over 2 times c to the fourth minus b to the fourth. I guess I could do my parentheses a little better there. So if it's a solid shaft, B is 0, so there is no inner radius. So this would be hollow. And J equals pi over 2 times c to the fourth. That would be solid. It is not always convenient to deal with the radius. Sometimes it's more convenient to deal with the diameter, because if you pick up some calipers or something to measure a shaft, you're not measuring the radius, you're measuring the diameter. So sometimes you will see this as let's label that guy. This is not how you label the diameter on a shaft, but we're going to do it this way. So if you had the diameters, the inner and outer diameter, I've gone with the outer diameter as capital D and the inner diameter as lowercase d. If you have those, then J is pi over, what is that, 64? D to the fourth minus lowercase d to the fourth. Is that right? I think that's right. Yeah. 2 to the fourth is 64. So that should work. Is that right? 2. Well, I think it's 64. If it's not, we'll come back and fix it. Or, and again, that's for the hollow. J equals pi over 64. It might be 32. 2 times 2. It might be over the 32nd power. I want to... Yeah, it's over 32. 2 to the fourth is 32. So you'll use one of these 4 since we're only going to do round shafts, either tubes or solid shafts. So now we've got a value we can plug in for J, one of these 4. Rho is just a distance somewhere, and T is some kind of internal torque. So let's set up a problem, a really simple one, and solve it, and see where we can go from there. I don't know if I want to bother with a, I don't know if I'll bother with the web work problem right now. Let's just make up one. So let's do a... I'm going to do a side view of our shaft here. And we're just going to say, so in the side view of a cylinder is just going to look like a rectangle. And let's just, for ease of dealing with it, let's mount it to something that doesn't move over here. Normally, you know, a shaft is mounted to a motor or a gear or a pulley, or, you know, something's making it turn or twist. Here, let's just mount it to a wall, and let's apply a torque. This is how I'm going to draw the torques. Either this would be, I don't know if this is a clockwise or counterclockwise torque. It depends on which way you're looking at it. You do have to decide, is this positive or negative? It's sort of like a moment. In fact, torques and moments are the same type of thing. Just in engineering, particularly mechanical engineering, we instead of calling them all torques, we limit the torque word to whenever you've got a shaft that's spinning or twisting, and we use the moment word whenever it's something that's causing a rotation about some point, but not a shaft rotation. So we just use different words to mean the exact same thing. If you were in a physics class, it's just all torques. All right. So you have to decide if that's a positive or negative, and it doesn't matter because remember, this is a shear stress, and shear stresses don't care which side, you know, are they sliding one way or the other way when they shear. Same thing if it's a torque that's causing a shear. It doesn't matter if it twists one direction or the other direction, it's going to have the same effect on the shear stress. So let's give this a number. Let's say that it's 50 foot-pounds. And let's give some other dimensions on here. Let's give it a length, although we won't need that for here, but let's give it a length of 1, 2, 3, 4, 5, 6, 7. That'll be 7, let's do 7 inches. So the length does not affect the shear stress, but if you imagine if this is 7 inches versus it's 7 meters, then clearly that's a much longer shaft versus the inch version of it. And that doesn't change the shear stress, but what it does change is when we get, this will be tomorrow, when we get to calculating angle of twist. So how much does this shaft twist from one point to another? Then the length matters, because the length of the shaft to begin with, a longer shaft is going to be easier to twist than a really short shaft, given the same torque. What we do need, though, is we need to know the outer diameter. So OD is outer diameter. And let's give it a relatively small one. We've got 50 foot-pounds. Let's say that's a half inch OD. All right, so let's build our equation, and let's do tau max equals T times C over J. Looking at our equation, I didn't point this out, but the maximum shear stress is on the surface. And if you look at the equation, it's obvious because C is going to be the largest value when it is on the surface. When C is the center of the shaft, then that's 0. There is no distance from the center. And the shear stress is 0. So shear stress is 0 at the center of the shaft, and it's maximum at the surface of the shaft. And it's going to vary linearly between those 2 points. All right, so the T here, now in our case, I only put one torque on our shaft. We'll build up to more complicated ones in a minute. The correct way to do this will be to go in and, cut this shaft open, draw our free body diagram, apply the external torque that we see, and then this little section of the shaft needs to be experiencing the opposite torque for it to be in equilibrium. So we will later on, Monday I think, we will have shafts that are spinning, so the torques don't add to 0 necessarily all the time. They actually do spin. But for this, for twisting, we're twisting the shaft, not spinning the shaft, then the torques all need to add to 0. They need to be in equilibrium. So this would need to be 50 foot-pounds of opposing torque. It doesn't matter positive or negative. We can say that the one that I drew external is positive, and the internal direction, that one's negative. We can do that, or we could do the opposite, and we'll still calculate the same number. We'll just get a plus or a minus sign difference. So the internal torque, I'm going to call the internal one a positive, just so I don't have the minus sign on it. 50 foot-pounds. We're going to convert those foot-pounds to inch-pounds, so 12 inches per foot. C is, remember, C is from the center to the outermost surface, so that's the outer radius, not the outer diameter, the outer radius. I have the outer diameter at ½ inch, so that puts the outer radius at 0.25 inches. Those inches will cancel out, those feet will cancel out. J, this is a solid shaft. At least I didn't say anything about an inner radius or inner diameter, so it must be solid. Oh, and I didn't mention a wall thickness either. So I do have the diameter equation here on the top of the screen. We'll use that one. Pi over 32 times outer diameter, 0.5 inches to the fourth. Oh, these inches don't, I'm sorry. Those inches don't cancel out. They multiply together. So that I have inches squared up there, inches to the fourth down here. Those inches cancel out, and I'm left with pounds over square inches. And let's see what number we get. Here's my calculator. 50 times 12 times 0.25 is 150 in the numerator. In the denominator, pi, I always lose pi on this calculator, there it is. Pi divided by 32 times 0.5 to the fourth. 0.00614 inches squared. So I've got my pounds per square inch. 150 divided by 0.0064 or 614. I get 24,430 pounds per square inch are my units, so that's PSI, which could also be 24.4 KSI. So that's of shear stress. So that's actually a pretty high number of shear stress. So let's look and see if I didn't give us a material. So we'll have to make that up. Let's find our material chart. No, not grading. Reference materials. Internet's being a little slow there. All right, material properties. Let's open this. Let's zoom in. So a lot of times I use this structural steel number. That will not work. 36 KSI is our tensile strength in yielding, or well, it says elastic. That is the same thing as yield. So that number is the point where if I exceed 36 KSI, this is tension. So pulling, or well, pushing in this case also, because the compression number is the same. But then if I exceed 36 KSI, then I have permanently stretched it out somehow. But we're looking at shear. So shear is empty. There's no number over here. So that means we use the model. We're using maximum shear strain. So that will be 36 divided by 2. This is the most conservative model we use. And so that's an 18 KSI. The problem is our calculated shear stress is 24 KSI. So we would yield this shaft if we made it out of that structural steel material and we put 50 foot-pounds on it, we would yield it. So that would mean, would we break it? Actually don't know. Let's see. The ultimate strength is 66 KSI. There's not a shear number there. Will you do the same thing where we take half, so 33? So we would not break it. We wouldn't exceed its ultimate strength, but we would permanently twist it to where it doesn't go back to its original shape. All right? I don't see any questions, so I'm assuming we're all right. Let's do one that's got a little more going on than that. These are actually pretty straightforward, so there's not a lot of complications we can add to this, but let's add a little bit. Let's say that we have a stepped shaft. So stepped shafts are pretty common when you're doing power transfer, because the steps, and what I mean by steps is this. This is an extreme step, probably more than we would ever have in real life. But there's the step. So that step is again not. Let me. That's just too much. I can't deal with it. So let's do this. So there we go. So there's our step. That step is usually there because there's a bearing, like a roller bearing, that has to sit on that step, or maybe a gear or a pulley has to butt up against that step and be held in place. So step shafts are pretty common. And let's say that we have one of these. Now I've drawn again, I have mounted it on some kind of fixed surface over here where most of the time these things are spinning. But we're assuming right now that we're just looking at shafts that are getting twisted, not spinning. Let's give this some dimensions and go from there. So let's say that this is, I don't know, that's 2-inch OD. And this one is a 1.5-inch OD. And on this step, let's say that we've got a gear put there, and it's applying torque to the shaft. So we've got a torque. I'm not going to draw the gear, but we've got a torque applied right there. And we've got a relatively large shaft here, 2 inches and 1.5 inch. I didn't put the units on there, but let's fix that. Inch OD. Let's say that this torque is, we had 50 foot-pounds here and a 1/2 inch, and it was not okay, but these are much larger. Let's do the other 50 pounds again. 50 foot-pounds. But let's add some others. Let's say that there's also another torque over here going a different direction for some reason, and it is 30 foot-pounds. I'm not really making this any kind of realistic scenario. It's just an academic exercise so we can do some calculations. And don't worry about where did the 30 foot-pounds come from. The 50 we kind of justified as there's a gear there that's maybe that's the input gear, and the 30 foot-pounds is some kind of output, and then it's attached to this wall, which is also weird. So it's a academic problem. So we have our, let's give it a material. Let's just use, let me look at our material list. We always use structural steel. Let's use something different. Let's use one 2014 T4 wrought aluminum. That's what we'll use. 2014 T4 wrought aluminum. All right. So now we have two torques on here, plus whatever the wall is doing. So the wall is applying some amount of torque also to keep the thing from moving or from spinning. So let's divide this into two sections. We'll have one section here. I'm basing the sections on kind of the same way we based the sections when we did the axial deformation. Anytime one of the things changed, so the diameter changes, or the torque changes, or the material changes, or something like that, then that'll be a new section. Actually, the material for stress calculations doesn't matter as far as the calculation goes. It matters as far as the performance, but it's not calculation of the stress doesn't change. Angle of twist it will. And then this will be our other section. All right. So let's look at the yellow section. So I've drawn my little cut line there. Let's draw our free body diagram of that thing. This one had 30 foot-pounds here. So for that yellow piece to be in equilibrium, I must have 30 foot-pounds going this direction. Whether or not that's positive or negative is up to you. We can call that one negative because last time we called this direction positive, so this direction would be the opposite of that. So we'll call this one negative. It doesn't really matter as long as you're consistent in the same problem. You don't have to be consistent across problems necessarily. Let's color this yellow so that we can make sure that we're keeping up with the right thing. Okay. Tau, this will be section, let's put some letters on here. A, B, C. So this is section BC. Tau in BC, and we're doing the maximum stress here. So the torque, let's write out our equation. Torque in section BC times the C value, so the outer radius, or diameter if you want to divide by 2, I guess, over J for section BC. And let's put our numbers in. The internal torque in section BC is 30 foot-pounds. We're going to convert it over to inch-pounds. We're going to multiply by the outer radius, which is half of 1.5 inches. And then we're going to divide by, again, this is solid. I haven't made any kind of hollow shaft yet. We'll do one of those next, and we're getting to where we've about done all that we're going to do with shear stress. So it's, we're almost done. Maybe we'll look at a web work problem. So pi over 32, we'll use the diameter equation, 1.5 inches to the fourth. Okay, these pounds cancel out. Oh, those don't, because I wrote the wrong thing. This should be feet. Feet cancel out. The inches end up being inches squared in the denominator, and I end up with pounds per square inch. And my number is 30 times 12 times 1.5 divided by 2, 270 in the numerator. The denominator, pi over 32 times 1.5 to the fourth. 0, 0.497. So hardly anything. That's inches squared for that. 270 divided by 0.497, 543.3 psi. So hardly any stress. But we have a, you know, 3 times the size diameter here with the even smaller torque there. Even though the 50 foot-pounds is over here, when we cut open section BC in the middle of it, it's clear that the torque is actually 30 foot-pounds. Let's do section AB. So I'm going to go to the middle of AB. I guess I should look up what is the yield strength and shear for this 2014 T4. So let's look at that before we get too far. 2014 T4, this one actually has a number there. So in this case, we will use the 24 KSI as the yielding shear stress, or shear strength, 24. And we have 543. So that's 24 KSI. We have 543 PSI. So that's certainly going to work. Let's do our blue section here, or cyan. I made it 5. Okay, so there's the yellow piece. Here's our cyan piece. We have 30 foot-pounds here. And we have the opposing direction, 50 foot-pounds here. So for this to be in equilibrium, you know, if I cut this section up and look at the equilibrium, I need another 20 go in this direction for it to be in equilibrium. So this larger cyan section actually has a smaller internal torque. So this is section AB. So the torque in section AB, or not the torque, but the torsional shear stress in section AB equals the torque in section AB times the outer radius of section AB over the polar moment of inertia of section AB. The internal torque we just found was 20 foot-pounds. This one, so I put a positive sign on the 30 internal going that way, so technically this is a negative. It is opposing the other one. That doesn't matter as far as shear stress goes, but it will matter next class, I think. Yeah, next class when we talk about which direction is it twisting. So we're going to talk about it twists so many degrees one way or the other. Then the positive and minus signs will be important to keep track of. So this is 20. Let's see if we can get these units right this time. 12 inches per foot. The outer radius is, well, let's see, what was it, 2 inches. But we want the radius, so the outer diameter is 2 inches. Radius is 1 inch. Divided by 2. Polar moment of inertia, pi over 32 times outer radius 2 inches to the 4th. So, again, technically this is a negative shear stress, but that's not going to matter. 20 times 12 times 2 divided by 2 is 1. 240 pounds in the numerator. Denominator, pi over 32 times 2 to the 4th. Oh, this is hardly anything. 1.57 square inches. So 240 divided by 1.57, 152.9 psi. So super small amount of stress. We knew it would be less than the other section because there was smaller torque and larger area. So we knew that would be less. So we're nowhere near failing our wrought aluminum shafts with these torques applied to them. All right. Let's see. I'm just checking the chat. I don't see any questions, so we'll move on. Let's look at web work and see if there's anything in there that we want to look at. So these would be an optional 3. I don't think I've assigned that to you yet, so don't be surprised if you can't see optional 3 just yet. Okay, so this problem is nothing but calculating the torques in the different sections. So what this one is, I'm not going to work this one, but what this one is, this is the optional 3 problem 1. This one is what we did when we cut the yellow section open and looked inside there. You would just cut section DE and, oh, well, TE is the torque in there, and so forth. So that's not a big deal. It's not torsional shear stress. It's just the torque in various sections. Let's see. This one's different. Let's do this. This looks like a fun problem. That'll probably get us enough torsional shear stress work. Well, let me see if there's an even better one, though. No. Not. That's angle of twist. So let's go back to that one. Let's do the one that I first wanted to do. Let's do this one. Gotta get, for some reason my shortcut keys don't do what they used to do anymore, so I have to do it manually. There's our picture. Let's go over here. And we'll plop it in here. All right. So I've got a little electric motor of some sort that is supplying, so we'll say inputting 525 Newton meters of torque to this shaft BCDE. These pieces are bearings. You have the little cross section of that first one that kind of shows a roller bearing in there. Those are irrelevant to what we're doing. We're assuming that they're frictionless, they're perfectly aligned, our shaft is not deflecting, you know, no problems with the bearings at all. So they're just there to show that this shaft isn't floating in space. So ignore those. The torque's removed. So what that means is that I've got this motor spinning these 3, they look like gears, and stuff is attached to each one of these gears. So each one of these gears goes and powers some other part of my machine. And according to my problem, whatever is being powered by C is using up 100 Newton meters of my 525 Newton meter input torque. D is 152. And E is 273. So if I add those numbers, here it is. If I add those numbers, 100 plus 152 plus 273, I get 525. So it is all the torque that's going into this thing is going out to the rest of the machine. That's generally the way we're going to approach these problems. In the real world, the bearings do, you know, scrape off some of the input power because there's some losses due to friction, things like that. But we're assuming that everything's perfect in our academic problem here. All right. So the torque transmitted by each section of the shaft. That's easy enough. Let's draw us a very simple version of the shaft. Doesn't need to be angled at the ends. There we go. Let's put, let's see, these points on here. So there's C, D, E, and then B is over here somewhere. So into the thing, we have the 525, and coming out, we have 100. I'm leaving off the units just to not make it too cluttery. 152 and 273. So for BC, we have 525 and then inside there we have 525 for it to be in equilibrium. So BC, 525 Newton meters. CD, we would have, oh, the 525 in, the 100 out, and then we would have another 425 out, so that we have balancing our torques there. So I have a total of 525 going in one direction, total of 525 going in the opposite direction. So the internal for CD would be 425. And then the last section, DE, my shafts are getting progressively worse here. There's the 525. There's 100. There's 152. And then this one, I would need an additional 273 in order for them to all balance. So the internal torque in section DE is 273 Newton meters. Part B, the maximum shear stress in the shaft. Here they told me it's a 34 millimeter diameter shaft. They didn't tell me a radius, internal radius, or hollow or anything. So we're going to assume it's solid. And that 34 millimeters is the outer diameter. So the maximum shear stress is going to occur on the surface. And it's going to occur in the section that has the highest torque. So it's going to occur in this first section here. That's where we had the 525 Newton meters of torque. So tau max, let's just put it over here, tau max is equal to the T max times C over J. J, this one does not have a stepped shaft. The shaft, at least the core of the shaft, is all the same diameter, all the same material, everything. So J is the same anywhere in this shaft. C is the same anywhere in this shaft. It's just it has different torques along the length of it. So the maximum torque that we had was 525 Newton meters. C will be 34 millimeters is the outer diameter, so we need to divide that by 2. Now I have an issue with millimeters and meters, so I have to convert over. The millimeters, 1 meter is 1,000 millimeters. So there we go. And then J, pi over 32, and then the outer diameter is that 34 millimeters. Let's go ahead and put that as 0.034 meters to the fourth. You do have to be careful here. So let's say that you put in 34 millimeters and then you raise it to the fourth power. You can't take that number and then say, oh yeah, I need to convert that over 1 meter is 1,000 millimeters. You can't do that. So you either need to convert it beforehand, like I did here, before you do the exponent, or you need to take your conversion factor and raise it to the same exponent that the number is raised to. Otherwise, you won't get the correct conversion. So I just converted it beforehand, and then we'll do the exponent after the conversion. So let's see what numbers these are. 525 is already in Newton meters, so that's good. Times 0.034, so 34 divided by 1,000. And then that's got to be divided by 2. So our numerator is 8.925, that should be newtons. And then our denominator is pi divided by 32 times 0.034 raised to the 4th power. So that's a really small number. 0 and a whole bunch of zeros. 1, 2, 3, 6 zeros. 131. That's meters squared. So 8.925 divided by 0.123456131 is, let's see, 129,771. Those units are newtons per meter squared. That equals, a newton per meter squared is a Pascal. So this is 68.13 megapascals, million pascals. So megapascal is 10 to the 6 pascals. Gigapascal, which you run across sometimes, 10 to the 9th pascals. So 68.13 would be our number here, hopefully. And then the location, where's the maximum stress, that was BC. So that, they don't get much harder. The only complicating thing could be, there could be two things that could be complicating it. One is its hollow shaft. So that just changes up the polar moment of inertia. You have to do pi over 32 times outer diameter to the 4th minus inner diameter to the 4th. So you could, that's one complication. The other thing that could maybe complicate it is if it's a design problem where you're trying to find the diameter or the inner diameter, the wall thickness, you know, something you're trying to find one of those, design the shaft given a maximum amount of torque in the shaft and some material properties. So let's check this just to make sure that we did it correctly. Yeah, those numbers are all the same numbers that we had. So I didn't plug them in, but I wrote them over on the OneNote page. And that is our stress. We had 68.13. They have 68.03. The difference there is in J. You know, I rounded off when I calculated J sometimes, particularly on that last one where it was such a small number. 0 point, a bunch of zeros, 131. There's some, even that 1 being rounded from some number, which my calculator didn't even give me any more digits than that. So maybe if I had MathCAD, I could get closer. But I ran out of digits on the calculator I was using. And so that is where those differences are coming from. But in general, a Pascal is a very small thing. A single Pascal is. So we're talking about fractions of Pascal, or percentage, fractions of percentages difference of 68.03 versus 68.13 million Pascal. Percent wise, that's a small difference. All right. I think that's probably good for intro to torsion. Next time we will do more torsion, and we will do angle of twist. So now that we can calculate if these things are going to fail, oh, I guess we should look at that. This problem doesn't ask for it. Oh, it doesn't give us a material though, but 68 megapascals is generally a small amount of stress. Let's see if I have, do I have a sheet? Here we go. So here is the same sheet we've been looking at, but in metric units. So there's that structural steel. The elastic strength in tension is 250 megapascals. So we had 68, 69 megapascals. Our shear strength, we do the same thing. The allowable here would be 125 megapascals, half of the 250. And we have 68 or 69 megapascals, so we have plenty of factor of safety, unless we just needed a enormous, factor of safety of 3 or something. We should be fine. All right, we will be back tomorrow at noon and do some more of this and do some angle of twist, which is similar to this, but it's more about calculating how much did something twist versus did it fail when it twisted or not.